Okay, good afternoon, everyone. Good morning, where you're dialing in from. I hope you're safe and well. And welcome back to the Astrea Bioseparations webinar series. Today we have a talk from Chloe Booth on process development. I'll hand over to Chloe in just a moment, but just to let you know, we will be recording this session and it will be available on demand, and we will email out the link out following the presentation. If you do have any questions during the presentation, please use the chat function and we'll try and get to these questions at the end of the session. If we don't manage to answer all the questions, we will reach out via email. So we will get back to you as soon as we can. Other than that, I'd like to hand over to Chloe, who will take us through the discussion and presentation on process development. Chloe, it's over to you.
Okay, thank you, Andy. So my name's Chloe Booth, and today I'd like to talk to you about chromatography process development. So the first question is what is chromatography process development? So this is where we look at optimizing the physical properties such as flow rates and column dimensions and the buffer conditions around your chromatography column run. The goal of this is to achieve the best possible performance for the chromatography column run when factoring in your individual process parameters. So why would you want to perform process development? There are a number of reasons why you may want to perform this, and these are three of the main reasons. It may be that you've found your adsorbent which is binding your target protein, but the recommended conditions aren't fitting your platform or your target stability. So for example, the recommended buffers may suggest that you elute with a low pH, and your target isn't stable at low pH. Therefore, you're going to want to find an alternative elution condition, which will still elute from the column, but in a range where your target is stable. Or maybe you want to insert an adsorbent into your platform process, and the loading conditions recommend aren't matching up with the state feedstock's in. Here you're going to want to see if your feedstock will work with the column as it is, and then if it doesn't, you may need to look at optimizing how you can load your feedstock onto the column with minimal intervention to your feed. Other reasons why you might want to perform process development is that you're not getting the specification, you're not meeting specifications for your column, which are commonly things like your binding capacity is too low, maybe your elution recovery isn't high enough, so you're binding your target to your column, but you're not getting it back, or the elution isn't pure enough. And the third reason why you may want to look into process development is you need to improve the efficiencies of your process. So it may be that you found you need a smaller column, as once you get to your final processing conditions, the column will be too large to fit into your process. Or it may be that you need smaller fraction volumes. Again, in your final process, if you've got very large volumes, it can be potentially hard to store, or it may put too much pressure on the further downstream process because you've got to factor in the time to process the larger volumes of your solution. It may also be that you need your column run to take less time, maybe to fit within a shift pattern, or to make it financially viable, you need to increase the number of cycles of adsorbents, the number of cycles your adsorbent is capable of performing. So what can we optimize? There are two main areas, and the first main area I want to look at are your buffer conditions. So the first step of your chromatography run is your equilibration and load. So you may want to adjust these to increase your binding capacity for your target, which will help you lower the column volume of your adsorbent, or it may be to help reduce the amount of non-targets binding to your column. Now, it's often that people don't want to optimize or adjust their feedstock. Therefore, this usually is one of the last areas that we look to optimize, and we'll look to other areas before we start altering our feedstock. Another area that we can, another area we can look at is our elution buffer. So we can look at changing our elution buffer to see if we can improve our target purity by seeing if we've got a more selective elution buffer, or to see if we can improve the target recovery. Again, if we can find a elution buffer that's more specific to our target, that can also help with that. While we're looking at alternative elution buffers, something else that we can also be looking for at the same time is if we've got anything that's suitable as a wash step. So while we're looking at our elution buffers, we'll be looking for something that has got a high amount of target with preferably low amounts of non-target. We can also be looking to see if we've got the opposite, so anything that's got high non-target with very little to no target. That way, we could potentially use those candidates as a wash step prior to the elution to help improve our purity of our elution that way. The final buffer step that we can optimize is CIP. So here we'll perform this if fouling is an issue and it's potentially affecting the number of life cycles that you're getting out of your adsorbent. Here we would look at a range of different CIP solutions, and that could be used in combination with multiple different solutions or in combination with hold steps as well. The other way that we can optimize the process is we can look at the physical conditions. So this means we can look at investigating things like the residence time, which is the flow rate at which we're loading at. So here we can look to try and improve our binding capacity by slowing down our flow rate or increasing our residence time, giving the target more time to bind to the column. Conversely, if we need to improve the efficiency of the column run and reduce the run time, we can look to see if we can reduce the residence time without having any impact on our binding capacity to reduce the runtime. If we find that we can't reduce the residence time without having an effect on binding capacity, we can then go on to investigate the flow rate for the rest of the column run. So we can look to see if we can have a faster flow rate for the equilibration, washes, elutions, while maintaining the flow rate across with the load and the post-load wash. When we're doing this, we would also need to take into consideration if we're going to get any problems with pressure on the column or if it's having an effect on our recovery of the other fractions. Finally, another area that we can look to optimize is the column dimensions, such as the bed height. So effectively here we're looking about what works best for your process, whether it's a long, thin column or a short, fat column. We've found that looking at this can help aid separation of target from non-target. We've also seen effects such as it being able to decrease the column volumes for fractions, take to eluting. So the next question is how do we go about performing the process development? They've got a number of approaches that we can use for this, and there are three main ones that we use. We've got standard iterative column runs, we've got screening plates, which are filled with a single adsorbent, which are our purer plates, and we can use a computer software design of experiment. We can use these alone or in combination with each other for optimal results, and each have their own advantages and disadvantages that I'd like to take you through next. So the first one is iterative column runs. This is where we perform a series of column runs investigating a condition at set intervals. So for example, if you wanted to investigate pH between pH 4 and pH 6, you might test pH 4, 4.55, 5.5, and 6. So the advantages of this is it's ideal for investigating very narrow experimental space. So if you've only got a few things, if you've only got a small area to investigate, a couple of column runs, and you've tested this whole space. This approach is also very close to how your final process is going to be, as it's run in a controlled column. This approach gives you large fraction volumes, which means that you don't need to limit the amount of analysis or pick and choose which tests that you're running, especially if you've got any tests that say need concentration and require a slightly larger volume. The disadvantages of this approach is that it's very time consuming if you have got a large experimental space to investigate. And that you generally have to address one condition at a time. So say that you wanted to look at the effects of pH and conductivity or salt concentration on your elution buffer. You would have to pick one and then the other. So you would start with pH and screen your pH range and find your optimal pH, which might be, say, pH 8, and then adjust your buffer at pH 8 for your different salt concentrations. This means that while you can potentially identify close to your best condition, you might not find the most optimal. So in the example that I just gave, you're looking at the effects of pH followed by the effect of conductivity. If you had been able to look at the effect of pH versus conductivity in combination with each other, you might have found that instead of, say, pH 8 at half molar salt, pH 7 at 750 millimolar gave you a much better result. It also means that you're not going to find the ideal response if it falls between the iterations that you're testing. So if you're upping in half pH units, and your ideal condition was at pH 6.7, you're going to be close at probably pH 6.5, but not on the optimal. The other disadvantage to this approach is if you are doing large numbers of column runs, it's very feedstock hungry. So if you're limited on feedstock, that could also be a potential problem. The next option we have is a screening plate. So this is a 96 deep well block, and each well has an individual drainage spout with a frit in the bottom. Into each well, we can add 0.25 ml of adsorbent to form a miniature column that's run under gravity. The advantages of this approach is that you can screen multiple conditions simultaneously, and this is really ideal for if you're screening unrelated conditions. So for example, you wanted to test different buffering salts, or you wanted to test different supplements to your elution condition. This approach also has a really fast turnaround time. The actual screen takes only a couple of hours. The time-consuming part for this is making up your buffers and running your assays, but these are things that you would need to do if you're running in a column anyway. Because you're using much smaller columns, you've also got lower feedstock usage. The disadvantage of this approach is that it does give you a small fraction volume. Therefore, you may need to limit the amount of tests or the tests that you're running. This approach is also better for trends than precise data. So it will tell you if something's working or not working. or it can identify roughly where your ideal conditions are. But it may be once you've found your rough area, you're going to want to go to a column run and perform a few column runs just to confirm which is the best condition. Final tool that I'm going to talk to you about is the design of experiment software. So this is a piece of software where you can tell it what continuous conditions you want to investigate, and you need at least two. So continuous conditions are linear ones like time, pH, conductivity. Here we tell the software the limits to which we want to test, and it helps us to design an experiment, and will give us a number of column runs that we need to go and perform. We go and perform these columns and then come back and input the data that we get from it, telling the software what we want to find out, such as we may want high purity, or we may want to maximize recovery of a given protein, or reduce recovery of certain problem proteins. And at this point, the software will then map the entire experimental space that we've investigated. So this technique can be used with either column run, can be used for column runs, or it can be used with the screening plate. However, the more precise the data, the better your outcome. Therefore, a column run would be preferable if you're finding out your final condition, whereas a pure plate would be more appropriate if you're scouting for your conditions that you want to further investigate. The advantages of this approach is that it will give you the optimal condition, which may not have been one of the column runs that you performed. It can also test multiple different conditions at the same time, which will help offer time savings. Which is one of the advantages. However, time can also be a disadvantage. This is an all or nothing result. You need to have run all the column runs that the model specified to get the result that you need out. Therefore, if you don't have sufficient amount of time to run all of those experiments, this approach isn't going to be appropriate for use. The other disadvantage of this approach is that you can't test a large range of non-continuous conditions, such as different buffering salts. And in addition, the results are only as good as the data that you put in. If you've got assays that aren't particularly accurate, it means that the result that you get isn't going to be particularly accurate either, so you may not be getting your optimal result. So what would you optimize, and how would you go about doing it? When we're designing our experimental approach, we need to think about a number of factors. What are the specifications that we need to add to meet? How much time do we have available? What is the experimental space that we can investigate? What quantity of feedstock do we have available to us to do this? And what assays are we using? Now we find that these things don't always align. There's always more to investigate than the time allows. And if feedstock quantity is a problem, then we need to pick carefully how we go about approaching the experimentation as well. So we may need to just select what our most pressing specifications are. And we're going to need to make sure that we're looking at our toolbox to make sure that we're selecting the most efficient way to reach as many of our goals as possible. So what we really need to do is think about what are our essential needs and what are our nice to haves. Is there data that we do need to test for eventually, but maybe we can leave that till later and not test that up front? So now I'd like to take you through an example of an elution optimization. Here, our aim was to find an improved elution condition for the purification of fab fragments from an E. coli spiked feedstock with fab-solvent F1P. We were happy with the process chromatography column run that we had for this, but we weren't happy with the purity of the elution fraction, which can be seen in line 6 of the SDS page. Here we're eluting with citrate at pH 3. As we were happy with the rest of the conditions that surrounded this column run, we decided to select a screening plate format to investigate an alternative elution or the addition of a wash condition by looking at a range of different buffering salts across their buffering pHs. So we loaded our column as we normally would, equilibrating with phosphate at pH 8, loading the E. coli, and then perform the post-load wash. The first thing that we did was then tested our range of different elution conditions. The different elution conditions that we were testing in this experiment was based on previous knowledge that we had from other experimentation that we had done, which was giving us an idea of what and where we needed to look. So here we went with an acetate buffer between pH 3.5 and 5 and a citrate buffer between pH 3 and 4.5, increasing in half pH units increments. And we also tested a tris acetate buffer at pH 4.5 as alternative elution conditions. We also looked at 3 different buffers at pH 9 as possible wash conditions. After we'd put our primary elution buffer on, we went in for a second elution with our existing elution condition, which was the citrate at pH 3, to see what remained on the column. So here we've got the SDS pages from the screen. On the first gel, we've got elution 1, which is where we changed the elution buffers. And on the second gel, we've got elution 2, which is where we went in and eluted with the citrate at pH 3 to see what remained on the column. So in lane 3, we can see our fab fragments as a marker for where they are. Highlighted in lane 8 is our control, which was the citrate at pH 3. So we can see here that we're getting a good amount of our fab fragments, but the elution profile is still quite dirty. The fractions that interested us the most from this were the acetate at pH 4 and pH 4.5 in lanes 5 and 6. So we can see in lane 6, the acetate at 4.5 still gives us recovery of our fab band and also significantly increases the purity, especially compared to the control. However, we weren't sure if we were potentially seeing a slight loss of fab fragments here. So therefore, the acetate at pH 4 was also of interest to us, as this looked like a slightly stronger band. And while there was increased impurity in comparison to the pH 4.5, there was still an improvement in purity compared to the citrate. Therefore, we went and ran these 3 conditions in a column run for comparison. So here in the first gel, we've got our starting condition with the elution just at citrate at pH 3. In our second gel, we've got the acetate at pH 4. And on our third gel, we've got our acetate at pH 4.5. So when looking at these gels, we can see for the acetate pH 4, we're getting a very strong target band for our fab band in our elution in lane 5. we can see that we're getting minimal amount of Fab band in the second elution with citrate in lane 6, and the purity we're achieving with the elution in pH 5 is a significant improvement on the purity from the citrate in the first gel in lane 6. Moving on to the acetate at pH 4.5, we've got the elution in lane 6. We can see this is improving the purity even further. However, the Fab band is also slightly smaller than the other two elutions, and we can see that we still have some Fab fragments on the column as it's being eluted in the citrate buffer after our first elution. Therefore, this gave us a choice of two possible different elution strategies. Acetate at pH 4 if we wanted to maximize our recovery but improve our purity in comparison to the citrate, or acetate at pH 4.5 if we wanted to focus on a purer fraction. So, in summary, process development can be a powerful tool to boost the performance of your chromatography column run in order to make it meet your needs. It can also be used to aid the efficiencies of your purification process. For example, it can help reduce your adsorbent costs, or it can help reduce the strain on your further process purification steps if you needed a smaller volumes to work with, or if you just needed to improve the purity to make it easier to reach your final goal purity. However, process development is a time investment, so you need to ensure that you are optimizing what is required for your process and you are using the most appropriate experimental technique to maximize your output. So thank you for your time, and are there any questions?
Thanks very much, Chloe. There are a few questions coming in. I'll just wait a couple more seconds to see if any more comes through. Just a reminder to everyone, if you've got any questions, please use the chat function, and we'll try and get to as many questions as we can. So there are a few come through then, Chloe. When you do the work on the troubleshooting, do you try to solve only one issue at a time, or do you tend to look at a number of issues together?
It depends what issues that we're facing. If we can combine multiple issues, especially if we're using the screening plate or a DOE approach, we will try and combine them because that is going to give us the most efficient use of time. However, if they are completely unrelated in the process, we would have to look at them separately because we don't want to compound the problem.
Sure. And does there tend to be one factor which helps more than others? For example, buffer type or conductivity, or is it very dependent on the ligand or the protein being purified?
It is very dependent on your adsorbent and on your protein. However, there are some things that we would definitely look at first, such as you mentioned, the pH and the conductivity. This is because they are usually the more ideal conditions because they are generally quite mild, and you want something as mild as possible in your process generally before you go and look at more extreme approaches.
Okay, and we got one last question then. Obviously, Astrea do a lot of adsorbent development alongside chromatography development. Does that typically work in parallel, or does one follow the other?
So we have actually incorporated looking at things like ligand density as part of our adsorbent development in combination with changing our load conditions to find the optimal loading. And that has seemed to have positive results in finding your optimal loading condition. There are some things that we can do in parallel once we've got to a certain point. So once we've discovered what our ligand density is, then we can carry on with the adsorbent development and then start the process development. However, sometimes we do need to wait for a ligand density at the minimum and before we investigate something like elution condition, because that can affect how tightly the protein binds to the column.
Okay, that's great. So thanks again, Chloe, for your very interesting presentation. Thanks for everyone for joining us today. As I mentioned, we have recorded the session, so it will be available on demand. In the meantime, if you get any further questions, then please don't hesitate to visit our website. And thank you all for attending. Thank you very much.